In this video, we're going to do an example where we show that the limit of a certain multivariable function doesn't exist. So specifically, our example is to show that the limit as xy goes to 0, 0 of the function xy over x squared plus y squared does not exist. So the plan for this type of question is we're going to actually make a substitution into the limit. We are going to let y equal mx, and we're going to show that the limit depends on m. So I want to draw a picture here and explain why that process actually establishes that the limit does not exist. So let's try drawing a picture here. Let's talk about, in our xy plane, let's look at a couple of different types of lines y equal mx. So we essentially want two lines that pass through the origin but with different slopes. Okay, so let's say that's one line in the xy plane. Let's call that y equal m1x, and we'll actually bring a second one into the discussion as well, so I'll draw that. Draw that now. Let's say this is y equal m2x is the red one. Okay, now let's go back to the blue line. So let's suppose we're traveling along these points, along this line and approaching the origin. And we want to track the values of our function being the xy over x squared plus y squared. We want to track those values as we go through those set of points. So let's say for this point right here, the value of our function is, let's say, this z value here. So let's just draw that. And as we go through the sequence of points approaching the origin, let's say this is what the values of our function do. Let's say they do this. Okay, they travel like that, they go up a little bit, they go down a little bit, and they approach, let's say, this value right here. Okay, so let's just draw an open circle there. So approaching that value. And to emphasize that these are the blue points, I'm actually going to draw just a little bit of shading here. We'll see in a minute why that might be important. But what we're really focusing on is this sequence of f values for that set of points. Okay, now let's do the same thing for the red line. So traveling along these points on the line y equal m2x and approaching the origin. So let's say for this point right here, the f value is up here. So I could draw that point, the corresponding point, in three-dimensional space by saying this point xy corresponds to this point xyz. Okay, and again, we're going to draw the sequence of f values that we're getting as we travel towards the origin. So let's say that we see some f values that are increasing. They come down, and as we approach the origin, let's say we're approaching that value right there. There we go. Okay, and then just to highlight the perspective here in three-dimensional space, again, I'm going to do this strange thing of just drawing some lines here, just so that we can understand that there are two different paths. And I just find doing this shading in helps our brain understand the perspective a little bit. Okay, so the idea is that as we approach the origin from two different directions, we're getting some inconsistency on what the value of f of 0, 0 should be. Is it supposed to be approaching the value indicated by the sequence of blue points? So is it supposed to be this value right here, or is it supposed to be the z value or f value indicated by the red points? Is it supposed to be that value there? We're getting this inconsistency. And so when that happens, what that's telling us basically is that there's either a hole or a jump in the function at the point xy equals 0, 0. So that's enough to tell us that that the limit as xy goes to 0, 0 of that function does not exist. So we let y equal mx, and if the limit depends on m, that's just a fancy way of saying, oh, that depends on which line you're traveling along or which path you're traveling along, and you're going to get different answers depending on which path towards the origin you travel along. Okay, so let's try the algebra then. So if we saw this question on a test or on an assignment, here's where we would start off. We'd say let y equal mx. And so when we say limit as xy goes to 0, 0, well, let's just recopy what we're trying to calculate. So limit as xy goes to 0, 0 of xy over x squared plus y squared. So that's equal to the following limit. We can now write limit as x goes to 0. The reason we can do that is we've said y equals mx. So as x goes to 0, that's also going to force y to go to 0. So we're safe now just to write limit as x goes to 0. And we're actually going to make the substitution y equal mx. So on top, we'd have x times mx. You could just write mx squared there. And on the bottom, we'd have x squared plus, if we square the y value, that's going to be m squared, x squared. All right, now to evaluate this limit, we're going to try to factor out the x squared from the top and the bottom. So we're going to say this is the limit as x goes to 0 of m times x squared over, that would be x squared times 1 plus m squared. And that way we can cancel that factor of x squared from the top and the bottom. And we'd have limit as x goes to 0 of now an expression that doesn't have any x's in it. So m over 1 plus m squared. And because there are no x's left in that expression, we can say, yep, this is just the constant m over 1 plus m squared. So the important thing here is that our answer here depends on m. And that's the exact thing that we said we were aiming for above. It means that the value of the limit depends on the path that you take towards your point. In this case, the point is 0, 0. And that's enough to tell us that the overall limit as xy goes to 0, 0 does not exist. Thanks for watching.